So, hello, my dear student. How are you? I hope all of you are well and doing good. So, I hope my voice is clear. Now, today is lecture number 13, and we are going building part 3. So, today we are going to discuss cycle electrode. So, let's start with what is the cycle, the welding pen, right? Specific, right? Which defines the number of which defines the number of minutes the number of minutes, find the number of minutes within a 10-minute period, right? Within a 10 minute, within a 10 minute, in a 10-minute, right? During which a given welder can say, during which a given welder, a given welder, a welder, right? A given welder, during which a given welder basically produce a particular way, given welder can safely produce, can safely produce, right? Safely produce a particular a particular, particular welding current, right? Welding, right? Let me explain the help of example, right? Example, let's say, there is a transformer, right? Now, there will be a rated, let's say, 150, a rated value is the, the transformer, right? And on the transformer, there will be a rate current, right? Rated current is what? Rated current, say IR 150 and 30% cycle, cycle is what? 30%. What is that? The meaning that can use 150 current for a welding, okay, 30% of 10, that is right. 150 current can drawn from farmer up to up to right, up to, after that, up to, for 7, right? After the 7, you can resume your welding process, right? You can resume welding process, my dear. Suppose that if you want to draw a current which is greater than, right, if you want to draw a current, right, if you want to draw the current, right, let's say I1 greater than 150, right, then what will be the duty, right? Then what will be the duty cycle? Let's say what? Rated time, right? Duty cycle rated time. Then what will be the time, or what will be the duty cycle? Suppose that if we will draw the current I2, which is less than 150 ampere, let's say 100 ampere, then what will be the safely, what will be the time period for which a welder can do a welding safely, right? Let's say T2. We have to find that T2. My dear, how can we find this? The thing is very simple. For that you have to apply this. For that you have to apply this thing. That is your current esquire. rated current square into rated, right? Rated time period or rated duty cycle into whatever current and whatever the time, right? So here you will get the desired, right? Here you will get the desired thing, right? Suppose that if you are providing this one, so you can write that I did, okay, square it equal to I1 square T. What the value of what? So let's find out the value of T1. IR is what? IR is your rated current is 150 ampere. So 150 divided by I is what? 200, right? Answer is square, right? Answer is square. So answer square in answer in rated answer in 3 1.6 here 1.68, right? 1.68 minute, right? 1.68 minute. Cycle is what? Cycle will be your 0.56, right? Duty cycle, find the duty cycle, okay, then it will be 0.56. Now, suppose that if your drawn current is what? 100 ampere. If your drawn current is 100 ampere, then what will be the duty cycle corresponding to that? Then how what Q can write that rated current square rated duty cycle I2 square into, right? So here I rated current, that is 150 square, rated time is what? 3, right? And here I2 is 100 ampere square, and this is, you will get the value of T2, then it will be 100 divided by 100. Okay, answer square answer into 3. So it will be 6.75 miles. What is the meaning? What is the meaning? 6.75. 0.75, the meaning 0.75 is that up to 6.75 minute, right? You can do the welding safely. After that, you have to stop. Okay, after that, you have to stop or duty cycle. Okay, two, you can write 0.675, right? 0.675. Okay, just leave it here. Just write down the time. Just write down the time. So I hope the point is crystal clear to, right, to you people. Now let's move to the let's to the okay. So we have discussed cycle. Now I'm going to discuss about the electrode. Right. Now I'm going to discuss about the electrode. So here I'm going to discuss about the electrode, my dear. So let me write down about the electrode. Write down about the electrode. Write down about the electrode. My dear, here electrode are of either non electrode, okay, either non electrode or consumable electrode, right? Either non electrode or electrode. This is what? This is your non consumable, okay, electrode. One is what? Consumable, right? Electrode, right? Non electrode. One is what? Electrode. Consumable electrode, right? Consumable electrode. And either you can classify electrode in there. Further, you can classify the electrode. Further, you can classify the electrode, consumable electrode in two types. One is coated electrode, coated electrode, coated electrode, and other is what? Uncoated, bare electrode, bare electrode, bare electrode, okay, or uncoated electrode, right? Uncoated electrode, right? Uncoated electrode. We have discussed about the coated and bare uncoated electrode in the previous. My dear, non-consumable electrode. Non-consumable electrode made up of carbon or tungsten, right? They are made up of carbon, are made up of carbon, right? They are made up of carbon, graphite, 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 or tungsten, or tungsten, right? Or tungsten. These are the electrons. Carbon and graphite are used for a right. Here, carbon and graphite are used for DC. Here, electrode is not constant. That's why the arc length remains constant. Arc is simple and is maintained, right? And easy to maintain. So, this, right? So, consumable electrode we have discussed, right? Consumable electrode we have discussed. Now, let's discuss the electrode. That if you are talking about, sir, coated electrode, then what will be the coated electrode coating? Let's talk about the electrode coating. Let's talk about the electrode coat, right? Let's talk about the electrode coating, right? Let's talk about electrode coating. Electrode coating. Let's talk about the electrode coating. My dear, electrode coating. Electrode coating, you have seen, actually this is the electrode, right? The electrode, right? This is right, this here. This electrode is covered with the material. That's right. This is what the right. What the right. This is coating, and here the filler metal. This filler metal. Filler metal. Right. Filler metal. Now, electrode coating. This coating is basically made up of powder. This coating made up of powder. Okay, powder mixture. Powder mixture. Powder mixture. So in this powder mixture, which type of mixture, right? Which type of write down type of mixture we are going here, right? So number one. Number one, the mixture is first. First, my dear, slag forming, slag forming ingredient, right? Slag forming ingredient, ingredient, slag forming, right? Number two. Number two is what? Arc stabilizing, arc stabilizing, right? In okay, dent. Arc stabilizing control the arc. Slag forming basically which form the slag. Arc stabilizing it form what? It form basically it maintain the arc. It makes arc stable, right? It makes the arc stable. Number three, right? Number three, that is deoxidizing ingredient. Oxidizing, oxidizing ingredient, dent, right? Deoxidizing. Number four, binding material, right? Here, binding material, right? Binding material. And number five, number four, and number five, there will be what? There will be some alloying constituent. Number five, we use alloying constituents to improve of weld. Alloying, alloying constituent, const, okay, alloying constituent, okay, alloying constituents, okay, to improve strength of weld, to, im- to improve strength of weld, strength of weld, right? Of weld. So these are the material, okay. These are the powder mix, the coating. I hope you understand this, right? You understand. Now let's just about some. Okay, let's about your have this electrode code. Electrode. Let's discuss about the resistance welding, right? Let's discuss about the resistance welding. So in resistance welding, yes. So we have discussed, yes, resistance, resist welding, resist. But in resistance welding, what we do, there will be a lap overlap plate. This will be the overlap plate, the over, right? And here, this is the electrode. This is the, so this is what, the electrode, electrode, right? These are the base plate. These are the base plate, plate, okay, right? Now, this is the, so with the help of electrode, we are going to apply, we are going to apply the, we are going to apply the pressure, and the current is supplied. My dear, here the electrode has resistance, here the electrode has resistance, what, R1, right? There is a resistance K in between electrode and workpiece is R2. There is a resistance of plate R3, right? There is an interfacial resistance the plate, that is what, R4. So similarly R1, R2, R3. Overall resistance. So the total resistance, my dear. So the total resistance here is what? Let me write down the total resistance. Total resistance. Total resistance, right? R is what? Twice of R1 plus R2 plus R3 plus R4. Here we keep the resistance electrode, still electrode and workpiece, and resistance workpiece. Resistance very small, right? So the overall resistance what R4, that is a internal, because we keep very small. Let me tell you the maximum value among them. Okay, among them is what? The maximum value will have only R4, and it will be micro ohm, right? Now you can compare if the maximum value of R4 is micro ohm, and these value are very small, so you can neglect it, right? Can neglect it here. So the basic principle is what? Here the basic very simple. Here the basic principle is very simple. Let me write down here. Let me write down. Right. The basic very simple. Let me write down here. The thing is that both heat and pressure are used because we apply the pressure, and the because of heat, basically heat is what I aspire RT, that much of heat at the interface produce produce this produce at interface at interface. Along with that, we are applying the pressure. Here you can see. Along with that, we are applying the pressure. So both heat and pressure are used, right? So you can write the principle of resistance welding. Both heat and pressure are used. Both both heat and pressure, both heat and pressure, right, are used. Both and pressure are what are used. So heat is generated by the electrical resistance of the workpiece and the interface between, right? Whatever the interfacial resistance. Here pressure is supplied externally, right? Here pressure is supplied externally and is varied throughout the weld cycle. Due to pressure, my dear, because you are applying the pressure, right? Due to pressure, a lower temperature is needed. Let me write down. Due to pressure, due to pressure, right? Lower heat, lower heat is required. Due to pressure, lower temperature. Due to pressure, you can write lower temperature, lower temperature, right? Lower temperature is lower temperature is what is, right? I hope the point is crystal clear. Lower temperature, if you compare with the if you compare to the other welding process, right? My dear, it is officially classified, right, as a liquid state welding. It is not a solid state welding, right? Here, here the process very fast, very rapid, so it's economical, extremely well suitable to automatic manufacturing. Here you can see that they are overlapped to each other. There is not required of any filler metal, no flux, and this point is quite important. No filler metal, no filler metal, right? No filler metal, comma, comma, no flux, comma, no flux, right? Flux, no flux, no shielding gas. Gas is required. No thing gas, shielding gas is required. No shielding gases is required. This process, right, my dear, this process, as I told you, this process is automatic process, right? This what automatic process. So here very high current and very low voltage is required. Okay, overall resistance very low. Basically the thing is that overall resistance very low, right? Let me write down. Overall resistance very low. Overall resistance resistance is very low, is very low, right? And because of that, my dear, because of that overall resistance very low, because of that very high current, very high current, right? Very high current, and current is up what? Current is up to very high means 1 lakh, up to 1 lakh ampere. Very high current and very low voltage is, and very low and very low voltage. So voltage is, right, very low voltage is, point is quite very important. Now when you doing, when you applying the heat at the interface, this is the overlap plate. Now at the interface, the nugget is going to be formed, a fusion zone, a fusion to be formed. What, my dear, this is a fusion, right? This what, this is a fusion, sun zone, right? What is right? This is sun zone where the where the where the metal are going to right. This fuse once this gets solidified, once this get solidified after solidification, after solidification, after solidification, solidification, after solidification. This is known as basically what nugget. This is what become this become nugget might become what come right nugget. Further, you can see that nugget of different shape. This nugget it may be a cylindrical shape. This nugget may be of cylindrical shape, maybe a spherical shape, maybe of oval shape, right? Maybe of oval shape. Let me write down here. The nugget may be of oval shape, right? Maybe of of cylindrical shape, of spherical shape, right? Spherical shape, spherical shape. Are you getting my point? Suppose that if the joint is going to be made it between the overlap plate, right? Overlap plate, joint is the overlap plate. Here you here the oval nugget, right? This is let's say cylindrical nugget. Here I'm trying to get. Here I'm trying nugget, nugget, and it may be possible that there will be a spherical, right? A spherical the overlap plate, right? In the overlap plate. So it is very important to understand these, right? So let's try some numerical, right? This thing with the help. Okay, my dear, let me write down a numeric. Let me write down a numeric. Yes, here, see, two metallic sheets of two. There is a there will be a two metallic sheets, right? Metallic sheet of 2 mm having a two having of having a two are welded in a lab joint are welded in a lab joint by resistance spot weld at the welding current of 10 kilo at a welding current of 10 kilo right 10 kilo m and welding time of 10 millis. Here is the welding 10 10 to the power right. Okay, 10 milliseconds. Okay, a spherical fusion. There is a spherical fusion. Spherical sun zone, right? Sun. There will be a spherical fusion. A spherical fusion zone extended up to full thickness. Spherical fusion extended up to full thickness. Extended up to full thickness, right? Extended up to full thickness of E is form of is formed, right, of each is right. So here some properties are given, like what? Like the ambient temperature, like the ambient temperature, not 90 Kelvin, right? Melting temperature, that is melting temperature is was right, and latent heat of fusion, latent latent heat of fusion 100 kilojoule per kg, 100 kilojoule per kg. Let's say. Are you getting the question? Right. Density. Density also gives, what is that? 7,000 7,000 per meter cube. Okay, per meter cube. Specific, right? Here, a specific heat also give specific, also give specific heat is also given. What is that? 800 K, 800 joule per kg, right? Per Kelvin. Right now, what you have to find out? You have to find out the melting effect. Also, the interfacial interfacial also give interface also give at 500, right? 500 micro ohm. Okay, so ohm will be 500 into the power minus ohm. Now you have to find out the melting. You have to find out the melting effect. The approach is there is a okay. What is the approach? My dear, we know that melting effect is which is required actually, which is required actually, right? Actually, right? Divide by heat which is required theoretically, theoretically, required theoretically. Now we have to work on these data, right? So the theoretical heat is what here. The theoretical heat here, the theoretical heat is what? I square RT, right? What is that? I. I is what? 10 kilo ampere. 10 kilo square R. 500 10 to the power minus 6 time T. 10 into 10 to the power minus, right? So what will be the value? Okay. What will be the value? Here, here, 10, 1, 2 square, 500 the power minus 500, 500. Now, my dear. Now, here the fusion zone, you have noticed that it is the spherical, up to, which is up to, right? This. Now, let's find out the volume of the nugget. Is what? This nugget, right? A nugget, a joint with the volume of nugget, volume, okay, of nugget, okay, volume of it is what? 4 by 3. Now, in short, I'm going to write volume, that is 4 by 3 pi r cube will be what? Here 4 by 3 pi r, here radius is what, 2 mm, 2 10 to the power minus, right, 2 into 10 to the power minus 3. Okay, so here 4 by 3 into shift pi into 2 into 10 to the power minus the power. Here the volume is 0.512 10 to the power minus 8 meter cube. Now mass of nugget. Okay, mass of nugget. Nugget. I can write M. What is the mass of nugget? That will be volume into density. Volume is there. That is 3.51 10 to the power minus 8 meter cube into 7,000 kg per meter cube. Let me see. It will be 2.345 into 10 to the power minus 4 kg, right? Kg. So this thing. Now, now you have a mass of the nugget, right? Now you can find out the actual heat. You can find out the actual heat. What is that? M delta T plus M latent heat, right? M into latent heat. So here mass is common, right? Bracket T plus latent heat. Mass is what? 0.45 10 to the power minus 4. Okay. C specific 800 joule per kg Kelvin, right? Change in temperature, that 1793 minus 93 1500, right? 100 plus latent heat 300 kilojoule. Okay, 300 kilo 10 to the power 3, right? So that much we come out. So here answer in 800 into 1500, okay, plus 100 into the power here, it will be come out 1.858, right? This is what actual. Now the melting efficiency, that actual heat, right, divided by your theoretical. So my dear, actual heat is 1.858 divided by theoretical heat is 500. Answer divided by 500, it comes out 0.77. Percentage, you can write 70.7%, right? So here the final answer is melting at 70.7%, right? 70.7, the final answer. I hope you understand the concept, right? Now let's move to another question. Let's move to the another question. Idea, there is one more question. A very good question is there of gate, right? Spot welding of two 1 mm thick sheet of steel. You are doing a spot welding. You are doing a spot weld. You are doing a spot weld, which are of 1 mm, right? Which are of 1 m, are of 1 m thickness, right? Sheet and having a density of 8,000. The steel having a density of 8,000 kg per meter cube, right? Successfully by passing a certain amount of current for a time of up to zero point 0.1 second. Here the welding time is let's say 0.1 second. Welding time is what? 0.1 second. Through the electrode. The resultant weld nugget form, or the resultant, this language I'm going to write, the resultant, the resultant weld nugget, okay, the resultant weld nugget formed is 5 okay, 5 mm in diameter, 5 mm diameter, 5 mm and 1.5 mm thick, and 1.5 thick, my dear, right? 1.5 mm thick. If the latent heat done here, latent of fusion is given, that is 1400 kilojoule per kg. 1400 kilojoule per kg. This is the latent heat, and the effective resistance in the welding operation, here the resistance micro, right, 200 micro. The current passing through the electrode, what will be the current? This find out, figure out, right? Have to be figure out. So let's solve this question. Let's solve this question. Now, solution. My dear, from this data, here that the nugget is what? Cylindrical. The nugget is what? Here, this is the it. See here, right? Having a diameter of what? 5 mm and thick, what? 0.5 mm. 1.5, right? Okay. You have to find out the current. My dear, first of all, find out the actual heat. That is I square RT. So I is not given. I is R is 200 into the power is 0.1. Now, sorry, not at the now H at, right? Is what? Mass of the nugget. Okay, mass of the delta T plus mass of the nugget, right? My dear, in this, right? So you can neglect some as overall it will become mass of. So first of all, we have to figure out the mass of the nugget. The mass of the nugget is volume of the nugget in volume is what? Volume is pi by 4 wire 5 into the power minus wire into height, that is 1.5 to 10 to the power the cube into density, that is what? Yes, 8,000. 8,000. This much will be the mass. So let me calculate the mass of the nugget, right? Let me calculate the mass of the nugget. Shift pi by 4 into 5 into the power wire 1 point the power. right? My dear, it will mass of the point 3 the power. Now the actual the what mass of the point 5 into the power into latent heat. What latent heat is 40 kilo the power, right? Sir, in 14 power, right, will become out how much? 3 to 9. Now efficiency will be H actual divided by H. My dear, this parameter is not given to us, right? This parameter is not given. If this parameter us now, then we can find out. Now in the question, wants the current approximated current, right? Approximated current. So we have to make some approximation. Sir, your mic have been problem. That really? Hello, Kumar. My voice is not clear. Hello. Yes. Hello. My voice is not clear. Yes. It's fine. Okay. So this thing is not given in the, and we need the approximated current. So what we do, right? There will be one thing. Assume that melting efficiency is 100%, or or loss in heat, right? Loss in heat is what equal to that thing we can assume, right? That thing we can assume. So according to this, you can write that actual equal to H theoretical, right? Actual equal to H theoretical. Now H actual will be what? Can see 329.86. H theoretical is what? I square into 200 into 10 to the power minus 6 into 0.1. So you will get the value of current. Will you calculate, Alok? Will you calculate this thing? How much will be the current? I square, right? How much will be the current? I think it will be 329.86, right? Divide by 200 into 10 to the power minus 6 into 0.1. The root of answer 4061. So 4061.15 ampere. So this is the approximated value of the current. Is that point is clear? Is that point is clear? Is this question is clear, my dear? Yes. Is this question is clear? Yes or no? Tell me. Yes or no? Tell me. Yes. Yes. Okay. One more question I'm going to solve in resistance welding. Right. One more question I'm going to solve in the resistance welding. So let me write down a question. One more question. A very good question. Listen me carefully. There will be a aluminum strip. This is a aluminum strip, right? This is what? This is the aluminum strip. This is what? This is a aluminum strip, right? This aluminum strip are going to be welded by resistance welding, and this aluminum strip have a thickness of what? 2 mm, right? 2 mm thickness, and we are doing a resistance spot welding, right? by applying the electric current. We are applying the electric current of 6000 ampere, right? 6000 ampere for 0.15 second. So the welding time is 0.15 second, my dear, right? The heat required for melting aluminum, okay, required heat, my dear, required heat, required heat for aluminum. How much? How much? 2.9 joule. 2.9 joule per mm cube. That is a heat required for the aluminum. And when you are doing the resistance welding,